So we're going to do a little review of Chapter 17. Did you see the, did I post a previous review? Did I point that out? Because I did one back in the spring when we were still sequestered. And I think it's a better presentation than the one I did last week. So you may want to take a look at that. If anything just doesn't click, or if I'm fumbling around, go to that one. I think it works better. But hopefully we can work out any kinks today that you might have.
Okay.
Let's see, where do I want to start? How about number 2? The only reason I want to start here is because discussions of spontaneity and entropy, they're all about probability. I mean, there's really nothing definite in it. When you first start chemistry, studying chemistry as a student, you hope that everything will be cut and dried, you know, and you can just learn a set of rules and do it. But eventually you find out that we're not as definite with our predictions as you may hope. And this sort of gives you a taste of probability. Doesn't have anything to do with chemistry. It's just we have 2 pyramid-shaped dice. Is that correct? Is that plural? Dice, singular. Dice is plural. Okay. Which outcome has the highest entropy? So the interpretation of that is which one is most probable. The best way to approach this one is to say, all right, suppose we roll one of those die and it comes up 1, or maybe it'll come up 2 or 3 or 4. We roll the other die at the same time, it might do the same thing. It might come up 1, 2, 3, or 4. So with this grid, there we go. We ask ourselves, which is the most likely? Yeah, highest entropy. So with this one, we've only got one probability here. With this one, we've got a 1 and a 2, and a 2 and a 1. So perhaps the best way to approach this is add them up. Which one gives you the total, the same total, the most number of times? So with this one, we got, yeah, that one's already going down. With this one, we have a sum of 2, 3, 4, and 5. And this one, we have a 3, 4, 5, and 6. A 4, a 5, a 6, and a 7. And a 5, a 6, a 7, and an 8. So which one has the most probable? Well, when we roll them such that we get a 5 total is the most probable outcome. Well, of course, I didn't just pull that out of the thin air. It's based upon the question. The question says the sum of the dice is 3, 4, 5, 6, 7. Which is most probable? And this one is. The summation of 5 is the most probable. That has the highest entropy. Okay, let's see if we can get some chemistry in here somewhere. How about number 9? See if I can get to it by paging. There we go. 9. Yeah, I'm going to get another marker. Yeah, that's better. Okay. Number 9. At 1 atmosphere pressure, liquid water is heated above 100 degrees C. So the temperature is greater than 100 degrees. The delta S of surroundings for this process, delta S of surroundings for that process equals what? Well, in this case, we don't have to give an exact value. In fact, we can't, because we only know temperature, we don't know Q. Remember our definition, negative Q over T. If we wanted to calculate it, we'd need the Q also. So it's just asking us, is the delta S for this process greater than 0, less than 0, equal to 0? If we were, let's take it from this point. Let's say, what if the temperature were exactly 100 degrees? What would be the, well, actually, at 100 degrees, the delta S is total is 0, because that's equilibrium. Let's see. Okay, I think the best approach to this one is to look, see, we're interested in what's happening to the surroundings. So let's draw a picture where we have the system and the surroundings. And the system is water. Well, actually liquid. And if it's above 100 degrees, it's going to water gas. So inside the system, we're converting liquid to gas. So inside here, where we have an endothermic process, right? Heat is going this way. So that means it's what? Plus. Okay? So we definitely have a value for Q, and we have a value for T, which would be greater than 373 degrees, 373 K. But let's focus on the sign. If Q is leaving the surroundings to make this system evaporate, then the delta S is going to be negative, because the Q is positive, the term is negative. So this one's going to be a negative delta S, less than 0. Okay, I hope that made sense. I kind of stumbled around a little bit until I found out what I wanted to say. Let's see. How about number 10? I have to scroll that one. Okay. At 1 atmosphere, liquid water is heated above 100 degrees. Okay, we're still at 1 atmosphere, and the temperature is greater than 100 degrees. Okay, so what's the delta S for the universe for this process? You know, that one, okay. Again, we're not at equilibrium anymore. This is greater than 100 degrees. So for our defined system and surroundings, the delta S for the universe is, in our terminology, the delta S for the total. Whenever you're not at equilibrium, then the delta S is not zero. We have to decide, is it negative or positive? And for any process that occurs, total or universe, if you're not at equilibrium, delta S has to be positive. If we say for the whole universe, I mean, that's an easy one. We just say, all right, so for the whole universe, it's got to be greater than zero. That's the definition. Delta S is always greater than zero. That's the second law of thermodynamics. So I think that's the simplest explanation for this one. It's greater than zero. I know in the review worked problems, I go into a lengthy discussion, but in the final analysis, it all boils down to this. What is delta S? That's the second law of thermodynamics. As long as you're not in equilibrium, then your universe and your total have to be greater than zero. All right, let's see. How about, well, number 11. Which of the following is true? Let's see, we're looking at definitions here. By spontaneous, we mean the reaction or process will always proceed to the right as written, even if fairly slowly. Okay, I'll agree with that. Increasing the temperature may speed up the reaction, but it does not affect the spontaneity of the reaction. Oh, when you change the temperature, you definitely change the spontaneity. Delta S surroundings equals minus Q over T, or if the pressure is constant, minus delta H over T. So anytime you increase or change the temperature, you change the spontaneity. So A cannot be true. Let's see, we mean B. We mean that the reaction or process will always proceed to the left, wrong. If we're saying spontaneous, we're meaning from left to right. If we say spontaneous left to right, then it's non-spontaneous right to left. So that was wrong. And this one looks like it's saying the same thing. Spontaneous to the left, no. But this one, okay. Always proceed to the right, okay, that's good so far. Increasing the temperature may speed up the reaction, and it generally affects the spontaneity of the reaction. Yes, it does. That's a true statement. That's the only one that makes sense out of that bunch. And since it's true, then E cannot be true. Let's see. How about, well, let's see, I'm skipping a few. Okay. Let's take a look at 34. Let's see if I can page down to 34. I'm going to get in there and scroll a little bit. There it is, 34. So we've got this reaction. Carbon dioxide and water makes methane and oxygen. That's a gas. Makes methane and oxygen. And it gives us a delta H. Delta H0, which means standard conditions, equals 803 kilojoules. All right, what this means is that the reaction is endothermic. In other words, you have to put heat in to get it over here. That's the first thing I noticed. Which of the following will increase K? K is the equilibrium constant. So which one will make K bigger? Well, if we write K, let's see what K looks like. They're all gases. So the K expression would be methane, oxygen. Wait a minute, is this balanced? Let's see, 4 oxygen, 2, 4, 1 carbon, 4 hydrogen. Okay, now it's balanced. Right, so now we can write this as 1, 2, and then CO2 and water. Okay. Let's see, what are our choices? Okay. I'm looking at the way I explained it here, and I wonder if there's an easier way. Let's take these and see and go move through A through E until I can't explain it any further just by what we have here. Decrease the number of moles of methane. A. Increase K is what we're looking for. Okay, increase K. If we decrease methane, well, it should be obvious. When you change the moles of methane, you can change the equilibrium position, but it does nothing for the value of K. K is a constant. The only thing that'll change K is temperature. So A and B increase V, same thing. You're changing the concentration by changing the volume. And it doesn't change K. Increase the temperature of the system. Okay. Increase T. All right. Now, I pulled out, for the first approach, I pulled out the this equation. Okay, and then I plotted it and say, if we plot that, 1 over T down here, and then log of K here, then this slope is delta H0 over R. So we want to move up and down on this thing. If we increase temperature, we decrease 1/T. So it moves it this way. So that increases log K, which also increases K. That would be a valid, if we go this way, then we have to go that way on this value, which increases K. So that's true based on that. But the simpler approach is to say, all right, for this reaction, if it's endothermic, that means delta H is over here. All right? If delta H is on this side, when you increase the temperature, you're going to drive the equilibrium in that direction. And that makes more of this, less of that, which increases K. So that's another explanation. This would be more quantitative, and this would be a qualitative approach. It's using Le Chatelier's principle, where heat is a term in the balanced equation. Right, so increase the temperature of the system. Yeah, that would work. All right. About 36. Let's see. I have to scroll that one. Yeah, we are skipping 35. 36. Okay, consider the gas phase reaction. NO plus a half O2. NO plus 1/2 O2, and they're all gases. We're given that at the beginning. Yields NO2. In a delta H, under standard conditions of negative 56.91 kilojoules. And K is given as 1.46 times 10 to the 6th. Well, at 25 degrees. That's the same thing as this. 25 degrees is standard conditions. What would the effect on the amount of NO present of compressing the equilibrium system to a smaller volume while keeping the temperature constant? You know, that looks like a Le Chatelier's question right there. What are our choices? The amount of NO will increase, NO will decrease, NO will remain the same. Answer depends on the value of K. Yeah, I think the key here is that the temperature is constant. So the K is not going to change. And the effect on the amount of NO by compressing the system at equilibrium. So if we compress this gas, well, actually, you can't compress one without the others. Compress the whole thing. So what you have is 1.5 moles on this side and 1 mole on that side. So if you compress that gas, what is its response going to be? It's going to try to make less gas. So if you make less gas out of this, that means you've got to shift the equilibrium to the right. So the amount of NO will decrease. Yeah. I thought this was supposed to be a discussion of entropy. And we're still on Le Chatelier's principle. It is what it is. In the final analysis, you can't separate chemistry into chapters. It all happens just as it is, and we try to figure it out. All right, let's move to 46. Let's see. Can I page it? No. All right, 46. Given the following data, calculate the normal boiling point for formic acid. So we're going to calculate the boiling point of formic acid liquid going to gas. Okay. All right, what are we given? Well, what's our approach first? If we want to know the boiling point, we want to know the temperature. The temperature at equilibrium. Of the system. We know this expression, delta S for the surroundings equals minus delta H over T. But we can also infer at equilibrium only. At equilibrium, the delta S for the system then would be the positive delta H over T. Because they're balanced. Any transfer has to be balanced by what happens to the surroundings also happens to the system, only in the opposite sign. So we can work the problem from this angle. Right? So if we solve this for T, let's see, T then would be equal to delta H over delta S for the system. And are we given that? Well, we have to calculate it, right? We're only given the enthalpy of formation, standard enthalpy of formation, and the delta S for each one of these. So for this reaction, we need to what is that thing up there? Oh, that's a cursor. Messing with my mind. What we need to do is calculate the delta V, these two values. So the delta H we know is product minus reactant. So minus 363. Yes, gas minus a minus 410 is the numerator. And then the denominator, we take 251, yes, product, 251. Now let's see. Right, there are no coefficients to multiply. I have to check myself there. Minus the 130. 1.1. Here we go. I think that's set up right. So this T, what we have to do is just resolve this equation. Right? I haven't lost you yet, have I? Sometimes I wonder. In other words, we're basing this equation upon this relationship with that equation at equilibrium only. Right? We just solve for T. These values are for the system. So if we don't know this relationship, then we're stuck. Can't go any further. But now we have delta H is product minus reactant. And delta S is product minus reactant for its standard values. So now we just have to resolve that equation. So this would be a positive 410 and then minus 363. And I get 47. And then here we have 251.1 and 130 is 100 and, let's see, did I do that right? Yeah, okay. You know what I didn't do? Just occurred to me. Looking at the units of measure. This is kilojoules, and that's joules. Whatever this answer is, it's going to be times 10 to the third. Because this is kilojoules. So this is times 10 to the third. Okay? All right. And this one is 121.1. This is Kelvin. I get 388, close enough. So the temperature is given in degrees C. So temperature in degrees C will be 388 minus 273 is 115 degrees C. So there's your boiling point, 115. I think the key to this problem is, first of all, we're at equilibrium at the boiling point. And then with the information we're given in the question asked, this is the relationship, except that that's delta S surroundings. We need delta S system. So at equilibrium, we know the relationship is this, is that, just change the sign. Now we're off to the races. We just have to remember, like I didn't initially, that this is in kilojoules and that's in joules, and that's typical. Entropy is very often given in joules as value, joule per mole K, and delta H's are usually kilojoules. So that's one place that can trip you up right here, is that unit. Otherwise, we would have come out with some fractional value of K, almost absolute zero, and that just does not compute. Okay, how about 52? Actually, I just remembered I never asked you if you had any questions about the review before I got into it. But as usual, you can stop me at any time. And we'll work out specific problems. Let's see, what did I say, 52? Okay, there we go. All right, we're going to calculate delta G, which is the standard Gibbs free energy of this reaction. So we've got water, gas, plus a half O2 gas. I think I saw that correctly. Yields hydrogen peroxide gas. And okay, at 600.1 K. 600.1 K. Now we have what? Okay. All right. So based upon this data, we can find out, let's work it backwards, right? Where are we actually headed? We need to find out delta G 0. Okay? If we're looking for the delta G 0, that's standard conditions. And there's one equation that we know. Let me see, is it in the useful? Be sure it's in the useful information. It's a derived version of Gibbs free energy that relates K. There it is. Minus RT log K. Minus RT log K. Now, the reason we can say this is because at equilibrium, the actual delta G for that temperature is 0. Right? The free energy at equilibrium has dwindled to 0. But these, under standard conditions, we can make this calculation. So what we need to find out is what is K for that reaction. All right, so that means that we've got to combine these two equations in such a way that we get this target. Now we're talking, well, not strictly speaking Hess's law, but we can combine these equations. All right, let's see. H2O2, that one is in the correct order. H2 gas plus O2 gas yields H2O2 gas. And this one is 2.3 times 10 to the 6th at that temperature. Let's see. The other one that yields water has hydrogen on this side. So we got to put hydrogen on that side for that one. And that puts water on this side where it needs to be. So we're gonna reverse the second equation. Okay. And this is equals K. And this one, now the K becomes what? The K has to be inverted. Yep. We have to say the K for this one is 1 over 1.8 times 10 to the 37. 10 to the 37 equals the K for this one. The problem is we've got too many waters. I mean, we only need one water. So we need a half of this one. Well, actually, that's not true. We need half of this one. But this one now becomes to the 1/2. Right? Anytime we multiply an equation by a constant, that becomes the power of the K to give us our new K. All right. So now we end up with this one. We're going to use this one like it is. This one's going to be water, half of this one, and half of this one. But what's this value? So let's calculate that one. So let's take the inverse of that one, 1.8 exponent 37, and then just hit the 1 over x key. All right? So that's 5.56 times 10 to the minus 38. And then we need to take the square root of it, because that's what 1/2 power means. Square root. Okay, so now we have a k for this equation is 2.36 times 10 to the minus 19. Okay. So I think we're going to be using this one. Let's check it to be sure. All right, let's see. We got water, hydrogen, cancels, after, before the arrows. Oxygen, we got a half on this side and a whole on that side. So this one's gone, and that leaves us with a half here. Okay, and then we've got this one. That one, that one, that one, that one. Okay, we're good. So we can bring them down, or we can just say, what can we do with this? Well, now, what is our new K? Remember, when you add equations together, you multiply the K's. So we multiply this K times that K. And see what we get. Let's see, I've already got this one in my calculator, so I just need to do the other one. I get 5.42 times 10 to the minus 13. Okay, so if we put this one right here, and then our R is 8. And where did it go? 3145. 3145 has to be this one, the one that has joules in it, not liter atmospheres, but joules. And this one, and then what's the temperature? 600.1 K. 600.1 K. So that one, this one times the natural log of that value. So if I take the natural log of this value, multiply it by 600.1, and then multiply that by 8.3145, and then change the sign, I get 1.41 times 10 to the 5. Okay, what did I do wrong? Oh, I didn't do anything wrong. This is in joules. Okay, so we take 3 powers of that one, makes this kilojoules, 1.41 times 10 to the 2nd kilojoules. And then to make it match what we've got up there, we just need to move the decimal to the right once, twice. There we go. 141 kilojoules. A positive 141. Okay. That took a while. I think the key to this one is to recognize what's the question, delta G 0. and that this is at equilibrium. Temperature doesn't change. If we're going for the K, that means the system has to be at equilibrium. That means the delta G is calculable from that value. Okay. Let's see. 53. All right. Consider the reaction. 2NO2 yields N2O4. All right. Let's see. All right, let's put what we know on the board. It's jumbled in that word problem. 2NO2 yields N2O4 gas. Okay. The delta H 0 equals minus 56.8 kilojoules, right? If the delta S 0 equals minus 175 joules per K. The temperature is, let's put it over here. Temperature equals 298 K, correct? Yeah. So it says we're taking, these two are mixed with an initial partial pressure of 2.4 and 0.42 respectively. So initially, N2O4 is 2.4 atmospheres. And NO2 is 0.42 atmospheres. Okay. All right. Now, what's the question? Which of the following statements is correct? Some N2O4 will decompose into NO2. N2O4 will decompose into NO2. Some NO2 will dimerize to form N2O4. That's what's happening. It's called dimerizing. You're taking two of these molecules, sticking them together. That's the di part. And making one molecule of N2O4. The system is at equilibrium. The final total pressure must be known to answer this question. Okay. So in order to know which way the reaction is going to go, this is not equilibrium. Right? So we can't use Le Chatelier. We have to find out what is, first of all, what's the K? Right? What's the K for this reaction? And then we have to calculate the Q and compare the two. We compare the Q with the K, then we know which direction it's going to move. Right? Because we're given some of both. Right? If we were only going to, remember your ice tables, if you're only given, if one of the components is 0, when you start, then you know which way it's moving. But in this case, we've got values for both, so we've got to calculate K, and then we have to calculate Q. All right, Q is going to be easy. Once we know what K is, then we can calculate Q because we know what K is going to look like, and Q looks exactly like it, only with the non-equilibrium concentrations. Okay, so we need K. how do we get K out of this thing? I'm wondering, the reason I'm pausing is I'm wondering if there's a simpler way than the way I did it here. We know that these are related by the Gibbs free energy equation. Right? Delta G equals delta H minus T delta S. We know that. Right? So we've got these values here, here, and here. We've got a temperature here, right? But that gives us delta G. That doesn't give us K. But we do know from our previous problem, actually, delta G0 equals minus RT log K. So now, if we can find this one, then we can plug it in here with the temperature and find that one. Okay? So you can do it as 2 steps. You can find out what this is based on that calculation, then plug it in here with the temperature and find that one. Or we can say if A equals B and B equals C, then A equals C. Right? So if this one is delta G and this one is delta G, that one is equal to this one. Minus T S. And we want to find out what K is right here. So if we say log K is equal to what? Well, it's delta H0 minus T delta S0 divided by these 2 terms right here, minus RT. There we go. Right. We can't cancel T because it's not, we can't factor T out of this expression. So now that we have that equivalence, we should be able to plug in some values. Right? Delta H. All right. I remember my units this time. This is going to be actually times 10 to the 3rd joules. Now we've got apples and apples that we can compare. Delta H then is minus 56.8 times 10 to the 3rd. I'm going to leave the units out. Minus 298K times delta S, which is minus 175. Okay? Then in the denominator, we have minus 8.3145 times 298. Okay. That gives us the natural log of K. Once we resolve that one, we can take the anti-log of it and find K. And we're one step closer to answering the question. Let's see, 56.8. Change the sign, exponent 3. Sure. 298. Sure. So 5 times. So this one is positive, that one's negative. I can add them together. And then the denominator is 8.3145. Divided to 8. So I get this one is 1.877. So K is equal to what? The anti-log of this number is E, because this is natural log, E to the 1.877. So now I just have to find E to the X. There it is. And this is 6.53. So that's K. Now we need to find out what, did I do that right? Yeah. Now we need to find out what Q is. So Q is equal to N2O4. This is going to be in atmospheres. Well, I probably should do it like this. Partial pressure of N2O4 at equilibrium. No, not at equilibrium, sorry. There. And then the partial pressure of NO2 squared. So we'll take this one, 2.4, and then we'll take this one and square it, 2, and divide it into that. And I get 13.6. Okay. Q is greater than K. If Q is greater than K, that means this is too big, that's too small. So it's going to move this way. It's going to cause decomposition of N2O4. Will decompose into NO2. Okay? It took a while, I know, but that's the only way I know to solve this one. All right, 53, let's see. Let's get another one marked here, I think. 56. Let's see. Yeah. Okay. Page. Yeah, there we go. Six. Okay, the following system at equilibrium, 25 degrees. PCl3 plus, yeah, chlorine, gas, yields. Actually, that should be a double arrow. 5 gas. And this is delta H 0 equals minus 92.5 kilojoules at 25 degrees C. Okay, if the temperature of the system is raised, the ratio of the partial pressure of PCl5 to the partial pressure of PCl3 will what? All right. Oh, okay. This system is at equilibrium. So if it's at equilibrium, what happens when we increase the temperature? Right? We can use Le Chatelier here because we're at equilibrium. This negative value means that it's exothermic plus 92.5 kilojoules. Right? Exothermic means the heat is a product. Okay? Now that we know that, if we increase the temperature, we're going to shift the equilibrium back this way, which decreases this and increases that. So the question is, the ratio of PCl5 to PCl3, partial pressure of PCl5 to PCl, partial pressure of PCl3 is going to do what? If it shifts this way, the numerator decreases, the denominator increases, and we get the ratio increases. Right? If the temperature of the system is raised, Oh, excuse me. That's the ratio. The partial pressure of PCl3 increases. Why does it say decrease? I missed my reasoning here. Okay, raise the temperature. The ratio of the partial pressure. Oh, that was right the first time. The ratio. I'm sorry, I got it backwards. The ratio decreases because this decreases and this increases. So the ratio decreases. Yeah, that's right. Your instructor got confused. That was 56. 50. 58. Okay. Let's see. Yeah, there we go. 58. The equilibrium constant for the dissociation reaction Cl2 to 2Cl was measured as a function of temperature. Okay, so here's the reaction. They have to be gases. Okay. And the equilibrium constant, K sub P, was measured at different temperatures. So you got a K sub P measured at different temperatures. You get different values here. Right? The K is going to change with temperature as a function of temperature. So actually, this is the X value and this is the Y value. Because we're controlling the temperature and the K response. A graph of log Kp versus 1 over T. Okay, there you go. So this reaction gives a straight line with a slope, negative slope, as we would expect, minus 1.651, minus 1.651 times 10 to the fourth, 10 to the fourth, and the y-intercept here is 14.51. Okay, that's the slope and the intercept. Okay, from this data, which of the following statements is true? This reaction is exothermic, endothermic, reaction rate is high, reaction is not spontaneous. Okay, remember the equation that we looked at earlier. Log Kp in this case is equal to negative delta H 0 over R times 1 over T plus delta S 0 over R. Okay. To answer A or B, we look at this part of the equation, the slope of the line. Okay? The slope of the line is negative. This value is negative. Well, okay. Yes. This part of the line is negative. This is negative. So this is equal to negative delta H 0 over R. R is a constant. So if the both are negative, then delta H is positive. That means delta H is positive, which is endothermic. Right? So that's endothermic. Can we say, while we're here, can we say anything about the spontaneity of the reaction? Well, let's see. Delta S 0 over R is equal to 14.51. So the delta S of the system is positive, which makes sense. We're going from a Cl2 to something less organized. It's positive. It's an increase in delta S. But that doesn't say whether it's spontaneous or not, because we don't know what the surroundings are. We don't know the total. We could probably calculate the delta G from here. But test taking technique. If you work down through here and it says none of these is a possible reaction, but you find one of them that is an answer, like this one, then you're done. That's it for the test question. You don't have to mess with D at all. Okay, that was 58. You know, we should be able to calculate delta G0. Just thinking about it. Minus RT log K. Right? If the slope, let's see, log K, well, we'd need, actually, anything we say about delta G is going to change with the temperature, right? And this thing is K versus temperature. So if we say it's spontaneous at one temperature, it may be non-spontaneous at a different temperature. So that one is, we can't solve that problem because we don't know where the stopping point is in this whole series of measurements. So for that reason, you cannot answer D with this information because we're not fixed at a temperature. We're moving through several temperatures. So that lets you off the hook for D. There's no way to answer D, not with this information. How about 59? Let's see, 59. For a certain process, we're not even saying what it is. At 300 K, delta G, this is not delta G0, this is delta G equals minus 10.4 kilojoules. And delta H equals minus 7.0 kilojoules. If the process is carried out reversibly, the amount of useful work that can be performed is. All right. This is kind of a trick question, just to see. You've been working these other problems, say, for a while, and you focused on, you got to do this, and then you come up with one of these. And to answer the question, the amount of useful work obtained from this equation, from this reaction process, is right there. Delta G. That is equal to the maximum amount of work that can be obtained, minus 10.4 kilojoules from this process. And the other key to this is that one, reversibly. Reversibility is required if you're going to assess maximum available work. Okay, that one was simple enough. Let's see, 59 and then, oh, excuse me, Nobody in the room? All right. 59 and, oh, that's it. Don't have any more marked. Okay. Let's look at a couple. How about, let's see, 19. Just because we have a few more minutes, I think. Yeah. Actually, we got a lot more minutes. 10:50. Let's go back, 19. Oops, too far. Oh, almost made it. Right. Just to reestablish our bearings. Freezing of liquid water at minus 10 degrees C. So we've got water. It's liquid, and it's going to solid. There we go. And this is occurring at minus 10 degrees C. So it's below its freezing point. All right. So when it goes from here to here, what about delta S? For that system, delta S should be decreasing. The number of microstates available to this system is decreasing as we go from liquid to solid. So this is negative. All right, the other is delta G equals delta H minus T delta S. At low temperature, this term becomes, I hesitate, but rather insignificant. As far, if we're going to assess the effect of these two, then this one, actually the effect of this one on that one, then this one as a negative really doesn't matter because this is a small value. So a negative, that's actually T is a positive even at that value. But it's a low temperature, a lower temperature. So a low temperature times this term means that this may be positive right here, that overall is positive. But it's very small positive. Okay? So that means, what is this? Well, for this system, what has to happen for this to do? It has to be exothermic. Right? This has to be negative. Heat has to leave. He has to leave that system in order for that to happen. So delta H is negative. So what about delta G? Well, if this is positive but insignificant, it's very small compared to this one, then this negative overwhelms negative, negative. They're all three negative. Okay? That's the reasoning behind that problem. All right. Let's see if there are any others in here that are worth looking at. What about okay. Let's look at 22. Yeah, that's all on the board. 22. So the following questions, so there must be more than one question referring to this one. 22. Oh, no. That's it. Just with that one question here refers to this information. So we've got 2 times iron plus 3 halves times O2 plus 3 waters yields FeOH3. Solid. Okay. Let's see if this is balanced. 2 irons. 3 plus 3 is 6 oxygens. 3 times 2 is 6 oxygens. And 3 times 2 is 6 hydrogens. 6 hydrogens. Okay, we're good. All right. What else are we getting? Delta H is minus 789. Kilojoules per mole. Temperature, 25 degrees in 1 atmosphere. Oops. C. And 1 atmosphere pressure. So these are standard conditions. We could put a 0 here because 1 atmosphere. Yes and no. We don't know the concentrations. We don't know that. Oh, yes, we do. Oh, yeah, we can say that. This is delta H on standard conditions. Okay, delta S values are given for each of these. And we're asked, what is the delta S for the universe? And by our convention, delta S universe is delta S total. So we're looking for this one, which is equal to delta S for the system plus delta S for the surroundings. Okay? In kilojoules per mole K. All right. So let's tackle the easiest one first. This one. Delta S surroundings is equal to minus delta H over T. So there's delta H, and it's already in kilojoules. So if we're working with, want to stay in kilojoules as our answer, then let's leave this one in kilojoules. So it's minus 789 divided by temperature, which is 25 plus 273 is 298. Okay. So now, let's see, 789, change that sign. And then 298. And this is 2.648 kilojoules per mole. Okay. There we go. All right, so we got this term right here. Done. How about delta S for system? Well, the delta S for system can be calculated from these values right here, right? Because this is delta S of the system, delta S for the formation of each of these terms, right? So we need 2 times that one, delta S system equals 2 times the one for iron 3 hydroxide, right? Because it's got a coefficient of 2 times 107. Now this is joules. We'll have to convert to kilojoules afterwards. Now we're going to subtract everything in the reactants. So 2 irons, 2 times 27. Okay. And then 3 halves oxygen, 205. And then 3 waters, 70. There we go. So we just need to resolve that mess of numbers. So 107 enter 2 times term. I'm going to put these together. 3 times 70 is 210. And then 3 halves of 205. Can't do that one in my head. Add that one to it. And then 27 times 2 is 54. Plus. And I'm going to subtract it from this one. Be sure I got everything here I need. There. So this is minus 3.575 times 10 to the second joules per mole K, which is equal to kilojoules would be divided by 10 to the third. So this is negative 0.3575 kilojoules per mole K. Okay, so we add these together. And yes, they're looking for an absolute value. So this one and that one together. Let's see, yes, 2.648. Let's see, I forgot to. Hold on a second. Here we go. And then, yes, add those together. So I get 2.29 here equals 2.29. Or rounded off, 2.3. Okay? And this is kilojoules per mole K. All right, that was 22. And let me search around and see if there's anything else interesting here that we haven't talked about yet. How about, let's see, this is going to take a little while. Yeah, it'll be a little bit of work. It might be worth it. 31. Too far. Here we go. 31. Given the following data, enthalpies of formation and the standard entropies for N2O4 as minus 20 kilojoules and 209 joules. Okay. Above what temperature is the vaporization of N2O4 liquid spontaneous? Okay, here's what we've got going for us. We're vaporizing N2O4. There we go. And the standard enthalpy, this one is minus 20 kilojoules per mole. Minus 20, yes, kilojoules per mole. And the standard entropy is 209 joules per kmol. Okay, for this one, I'm putting this stuff up on the board because it's such a jumble in the word problem. Can't make sense of it until you get it out here, away from that problem. 10 kilojoules per mole, delta H, 0, equals 10, yes, kilojoules per mole. And the standard entropy is 304.2 joules per kmol. Okay. Above what temperature is the vaporization of N2O4 liquid spontaneous? So we're looking for the temperature at spontaneity for that process. All right. So where are we headed with this? Well, I'm looking to see if there's an easier way to solve this. You know, what's the boiling point of this liquid? At what temperature does it boil? In other words, that we want the equilibrium state in which this one, no, the equilibrium state where this one is equal to 0. Then, if we increase the temperature above that, then we will get spontaneity. Okay, so in order to do that, we need, let's see. In order to answer this, the relationship here is delta S for the system is equal to delta H, 0 divided by 10. and that's a positive. So what's the delta S for the system? The delta S for the system is this one minus that one, right? Well, actually, let's find out what the enthalpy is first. So the enthalpy is this one minus that one, which is 30 kilojoules. Delta H equals 30, right? 10 minus 20, 30 kilojoules per mole. And you know that one. And that means it's endothermic. The delta S for the system is equal to this one minus that one. So 304.2 minus 209.0 is equal to, let's see if I can do this in my head, 2, 9, 5, 9, 95.2 joules per K mole. There we go. So we know this one, and we know that one. So we should be able to find this one, right? Yeah. This one needs to be converted to joules, though. 30,000 joules. So let's solve for T. T equals delta H 0 divided by delta S system. Okay? And delta H would be 30,000 joules per mole. And the delta S would be 95.2 joules per K mole. So 95.2 into 30,000. $95.2 divided. That's 315. Okay, that's the boiling point. So what's degree C? Well, temperature is also equal to 315 minus 273 is 42. 42 degrees C. So that's the boiling point. That's equilibrium. So any temperature above that would be a spontaneous reaction. Why? Because this is endothermic. You put energy in, you're going to improve the spontaneity of the reaction. In other words, that term goes on this side. If we increase the temperature, we drive it to the right. So anything above 42 degrees, above 42, here we go. Okay. Let's see. We might have to quit early today. Unless I can come up with something. Let's see.
Oh my God, I lost it now. I don't have it anymore.
Maybe one more.
Okay.
This one should be fairly simple.
All right.
At 40. And, oops, too far. All right. For these three reactions, I'll save us time. I'm not going to write them up there. Which of the following will have a positive value of delta S? And remember when there's no subscript, the delta S stands for the system. So with the system, should the delta S be positive or negative or unchanged? We're looking for positive. So we've got 1 mole here and 1 mole there makes 1 mole there. This one's negative. It's going from 2 moles to 1 mole. Actually, it's going from a solid plus a gas to a solid only. Actually, that's the better approach. We're getting rid of this gas, which is high entropy. So we're combining it with this to make a solid low entropy. So this one's negative. Right? This delta S is negative 2. Let's see, we got all gases. Okay, now we can look at moles. 2 plus 3 is 5, going to 4. That's a decrease also. So delta S0 is negative here. Now we're not saying anything about the spontaneity of the reaction because we're only looking at the system, the delta S for the system. This solid is going to aqueous solutions of the ions. That delta S is positive. We have many, many more microstates for these ions than we do for this solid in that crystalline state. So 3 only is a positive delta S. If a sneaky instructor were to say, take this one and just say, we'll have a negative value of delta S, then you'd have 1 and 2. Okay. And 41 caught my eye. Let me see if it's worth looking at. Break my promise. Largest increase in entropy. Well, the largest increase in entropy would be going from, let's see, there's a solid gas to solid. No, that's a decrease. Liquid, solid, solid, no, that's a decrease. That's a decrease. Decrease, decrease. No change. 2 to 2. Solid to gas. Yeah, that would be an increase. Okay. I think that's about as prepared as it's going to be.